Welcome to this lecture series in linear algebra. In this lecture, we'll look at the notion of direct sum of two vector spaces. We will look at both the internal and the external direct sum. We'll come to that. But what we need to know broadly is the notion of finite dimensional vector spaces. This whole lecture series is about finite dimensional vector spaces. Even if I do not mention somewhere that a vector space is finite dimensional, it will be assumed that it is finite dimensional unless otherwise explicitly mentioned. Okay, and of course we need to know what is meant by dimension, basis, linear independence, all those things we need to know. And we need to recall this operation that one can perform on two subspaces. If U and W are subspaces of a vector space V, then we can define the sum of those two subspaces as this thing, and one can easily verify that this itself is a subspace. Okay, so let's move on. Here are some problems for practice. This is an important problem. We will prove this later separately, but as of now, this should be doable with the tools in hand. Basically, this is something that one can prove using the extension theorem that we saw, that any set of linearly independent vectors can be extended to a basis. It's a very important fact. And of course, these two exercises are linked, and this is a separate nice exercise. Okay. So first we will define what is called the internal direct sum of two subspaces. So suppose V is a vector space, again finite dimensional, I am not writing that, and some base field F that is also hidden from writing. Suppose U and W are two subspaces of V. We say that V is the direct sum or internal direct sum of U and W if for all vectors in V there exist unique vectors in U and W such that the vector V is the sum of U and W. Right? So that's the definition. To flesh it out, what this is saying is that suppose we find that U1 plus W1 is equal to U2 plus W2 for some vectors U1 in U and U2 in U, W1 in W and W2 in W. If this happens, then we must have that U1 is equal to U2 and W1 is equal to W2, and that this sum of these two subspaces is the entire vector space V. So each vector can be expressed as a sum of one vector in U and one vector in W. So if you delete this uniqueness condition, all this is saying is that the vector space V is this thing. But with the uniqueness condition, it says that if such an equation holds for some U1 and U2 in the subspace U and W1 and W2 in the subspace W, then we must have that U1 is equal to U2 and W1 is equal to W2. So that's the definition of direct sum. We say that V is the direct sum of U and W if this happens. Okay. So this was defined for two subspaces. We can generalize this to multiple subspaces. We will look at examples, but first let us get a few things out of the way. So let's define the notion of internal direct sum for multiple subspaces. This time we have some finitely many subspaces of a vector space V. Again, we are assuming this is finite dimensional, although that's not very important for this definition. We say that V is the direct sum of the given subspaces if one can guess if for each vector V in V there exist unique vectors in the subspaces U1 up to Um such that you can write V as the sum of U1 up to UM. So it is an immediate generalization of the previous definition. And one thing I forgot to mention, what is the notation? So when we have, if suppose V is the direct sum of U and W, we write V as U and then this funny plus and a W. And here we write V as U1 funny plus up to UM. Right, so that's just a notation to express all this in one shot. Again, before looking at examples, we just need to get one thing out of the way. This is a criterion to decide if a vector space is the direct sum of two given subspaces. So suppose U and W are subspaces of a vector space V. Again, this is assumed to be finite dimensional over some base field F. Then V is the direct sum of U and W if and only if these two conditions are met. First condition is that U and W together span the entire vector space. And the second is that the vector spaces U and W should not intersect, or rather they should intersect only trivially. Of course, they will intersect. Any two subspaces will intersect in the origin, meaning the zero vector, I shouldn't call it the origin. The zero vector, I should also maybe make curly braces around it. Yeah, so the two subspaces intersect trivially. So let's prove this. Very easy to prove. So there are two directions to the proof. First, assume that V is the direct sum of U and W. So assume this. Then we need to prove 1 and 2. But 1 clearly holds. Immediate from the definition of direct sum. 1 clearly holds. Let's argue 2. So suppose for 2, suppose we have some vector in the intersection. We want to show that V is 0. We want to show that this is 0, but not that. But V can be written as V plus 0, and it can also be written as 0 plus V. So when we write it this way, think of this as a vector in U, and that is a vector in W. And when we write it this way, think of 0 as a vector in U and V as a vector in W. And now by definition of direct sum, there should be only one way to write V as a sum of a vector in U and a vector in W. It just forces that V is 0. So thus, V is 0 and we have proven 2. So this direction is done. So now assume 1 and 2. And now we want to show that V is the direct sum of U and W. So let V be a vector in the vector space. Since 1 holds, we do have, one can write this as a sum of a vector in U and a vector in W. Suppose we have two different ways. So say V is equal to U1 plus W1. And that is also equal to U2 plus W2 for some U1 and U2 in U and W1 and W2 in W. What do we need to do to finish the proof? We want to show that U1 is equal to U2 and W1 is equal to W2. Once we do this, we will be done. But note that. But from this equality, just look at this equality, we have U1 minus U2 is equal to W2 minus W1. Right? We just shuffle things around. Take this to the left side, take this to the right side. This is equal to that. Now this is a member of U because U is a subspace and difference of two vectors in a subspace is all again in the same subspace. So this is in U. By the same reasoning, this is in W. Therefore, this is in both U and W. And hence this must be 0 by our assumption that 2 holds. So U1 must be equal to U2 and by the same reasoning W2 must be equal to W1 and we are done. So finish this. I have said it in words, you can write it down. Okay. So this is a criterion to detect if a vector space is the sum, or rather the direct sum of two given subspaces. And now let us look at two very simple examples which will illustrate the point. So consider these two subspaces of R3. Of course, I have drawn a rectangle, but what this is supposed to suggest is the plane that is passing through the origin. This is a plane passing through the origin, and similarly, this is another plane passing through the origin. A little bit of thought will tell you that let's call this U and let's call this W. You can easily see that U plus W is the entire R3. That is not hard to see. But they intersect in a line. And a line is a non-trivial intersection. Hence, R3 is not the direct sum. So this does not hold. This is not R3. I mean, R3 is what I'm trying to say with this equation is that R3 is not the direct sum of U and W. It is a sum of U and W, but not the direct sum. However, in this example, we have, let's say this is U and this is W. So U is this line passing through origin and W is this plane passing through origin. And here you can easily see that this is the case. So spanning is fine. Suppose I want to write this vector as a sum of a vector in W and a vector in U. You just kind of go parallel to U, hit W. This is a vector in W, and this kind of you just think of as a vector in U because it's the translate, so to say, of this guy. So this plus that is your chosen vector. So that shows that U plus W is R3, and intersection is clearly only the origin, and hence R3 is the direct sum of this and that. So very simple. And now let us look at the notion of complements. So let U be a subspace of V. We say that a subspace W of V is a complement of U if V is the direct sum of U and W. That's the definition. So let's look at an example. We have R2 and suppose this is U. Not happy. So let's say this is U. Now any one-dimensional subspace that does not intersect U away from the origin, which is basically any subspace that is different from U, any such thing serves as a complement. So this is a complement of U, that is a complement of U, that is a complement of U, this is a complement of U. So there are multiple complements. And yeah, so the notion of a complement is not hard. It's also a very simple fact that every subspace of a, again, finite dimensional vector space has a complement. In fact, it will have many complements in general. Okay, so let's prove this. Very easy to prove. So let U be a subspace of V, where again V is a finite dimensional vector space. Let U1 up to UM be a basis of V. Basis of U, sorry. And yeah, before I wrote that, I should say, suppose U were equal to V. If U were equal to V, one can easily find the complement of U. It is basically the trivial subspace. So V is the direct sum of V and the trivial subspace. So we may assume that U is strictly contained in V, which in other words means that the dimension of U is smaller than the dimension of V if you solve the exercises. That is same as saying that dimension of U is less than dimension of V. Okay, so fix a basis of U. Now by the extension theorem, we can find B vectors in V such that the appended list is a basis of V. Why can we do this? Any list of linearly independent vectors can be extended to a basis, and a basis of U is after all a linearly independent list of vectors in the vector space V. So we can do this. Okay, this is a basis, and now just define W as span of V1 up to Vk. Perhaps a better notation was W1 up to Wk, but up now I have done it, so I have to just continue. So define W as that, and now just note that V is the direct sum of U and W. So that I leave as an exercise. Why is that the case? Just use the criterion. Just note that U and W intersect trivially and that together they span the entire vector space. So every subspace has a complement. And now finally, we will talk about the external direct sum. So suppose U and W are vector spaces over a field F. So they are independent, they are vector spaces. They are not subspaces of some common vector space. They are just vector spaces in their own right, or the same base field. So it's not like this is a real vector space and this is a complex vector space. No, they are both over the same base field. Then we can form the external direct sum of U and W as follows. So we define the external direct sum of U and W as a quadruple, the Cartesian product of U and W. The base field remains the same. We will define an addition operation and we will define a scaling operation. So the addition operation does what? Addition operation, let me call this V so that it's not hodgepodge. And the addition operation, of course, takes a pair of vectors and produces a vector. I mean, right now it's not even legitimate to call them vectors, but I hope you understand what I'm trying to do. So how do you add U1, W1? This is a point in V, plus U2, W2. This is again a point in V, and this is defined as that thing. Again, do not get confused. This plus is borrowed from the vector space structure of U, and this plus is borrowed from the vector space structure of W, and this plus is what we are defining. So this is defined to be equal to that, and scaling operation alpha U, W is defined in that way. So I should write for all U1, U2, etc. And I'm not doing that. Okay. So this is how we define the addition and scaling operations, and you can check that this is a vector space. Check that is a vector space over F. Is a vector space. And yeah, what do I want to say? Yeah, so notationally what we do is we write this as U and this funny plus W. So this may cause confusion because this funny plus was used in a slightly different context, but as you progress into linear algebra, you will agree that this is not really a bad clash. It's a very good clash of notation. So when we form the external direct sum, we use the same funny plus. Okay, and here is an exercise for you. Exercise. Show that dimension of the external direct sum is sum of dimensions. Okay, you just have to locate a basis and you will see. So I think that's it. Yeah, so with this I want to end this. As usual, like, comment, share, subscribe, and I will see you next time.